In this video, we're going to become introduced to the fundamental theorem of calculus in the process of antidifferentiation. And we're going to begin by looking here at this first problem where on the left-hand side, we're given the graph of some velocity curve. And the horizontal axis represents some units of time. Let me label that here. And if we were going to try to write an expression that represents the displacement of the particle, so over here on the right-hand side, how would I go about doing that? In order to find the displacement of a particle, we would have to relate the velocity of the particle and the time. So displacement is equal to velocity times time. So displacement is basically you compare where you ended up to where you started at. And in order to find the displacement when I'm given the velocity curve times time, I need to start thinking about, well, wait a minute, if I'm going in this case from 0 to 10, the displacement would be the area up underneath that curve. And so since the displacement would be equal to the area up underneath the curve, we've been finding the area up underneath the curve and relating that to a definite integral. So in this picture on the left-hand side, the area up underneath the velocity curve would be the definite integral from 0 to 10 for my velocity function of t dt. And our displacement, remember the displacement's our overall change in position. So if I'm looking at my change in position from 10 to 0, I would take my position at 10 and subtract my position at 0, and they would wind up equaling the same thing. All right, let's look here at this next part. Suppose a car's position is given by this expression here, where t's in seconds, and we're looking at the closed interval from 0 to 10. I want to figure out, well, what is the position of the car when time is equal to 0? So the position when time is equal to 0, I would simply just put 0 into that equation that's given, and we get 25. And the next part, what is the position of the car when time is equal to 10? I would just go put in 10 for the t in for all of that. So I'd go find s of 10. We plug in 10, and we wind up getting 475. So the overall displacement of the car from time is equal to 0 to time is equal to 10, what I would do is I would take my position at 10 and subtract my original position from it at 0. And so 475 minus 25 would be my displacement. So 450 is the difference from start to finish. All right, let's look at this last problem here on the bottom right. Use our calculator to determine the area up underneath the velocity curve from 0 to 10. All right, well, in order to do that, we would have to first find our velocity function, which velocity would be the derivative of my position function. So I'd take the derivative of s. And so the derivative of s, we would wind up getting 3t plus 30. And so what we would do to find the area up underneath the velocity curve is we would simply integrate our velocity function from 0 to 10. And so of 3t plus 30 dt. And we would type that into our calculator, and we would get a value, and we get 450. Now, what do we notice about that number 450? So when we integrated our velocity function, we got 450, which ended up being the same thing as our displacement over that time. So the difference between my ending position and my starting position, which is a very interesting concept for us that I'm going to elaborate a little bit more on. What we saw was that the displacement equaled the signed area up underneath the velocity curve. So we were looking at the displacement from time was equal to 10 to when time was equal to 0, and that ended up being the area up underneath the velocity function, or the signed area up underneath the velocity function from 0 to 10. So v of t dt. And let's generalize this process a little bit more. Instead of just looking at overall when time is 10 and time is 0, I could look at this and say, all right, well, let's say we were talking about any time interval from A to B. So my overall displacement from A to B would be s of B minus s of A, which would equal the signed area up underneath the curve from a to b, or the definite integral from a to b for v of t dt. Now, we could even go one step farther here. Remember the relationship between position and velocity. Velocity is equal to, so velocity is equal to the derivative of my position function. So let's just, instead of talking about position and velocity, let's relate this to any function f. So if I found the area up underneath a rate curve, which is basically the derivative function, that is going to equal the difference in the y values of the functions whose derivative this f prime is representing from f of b minus f of a. And this takes us to the fundamental theorem of calculus. The fundamental theorem of calculus is telling us that if f is continuous at every point of a closed interval from a to b, if I found the value of the definite integral from a to b for f of x dx, that's equal to f, capital F is representing the antiderivative of this function here. So it would be equal to the antiderivative of f of b minus f of a, which in context of what we had written in red, which is makes a little bit more sense to us at this stage in the game, is that what is inside of the definite integral, this function, is the derivative of this. So the derivative of capital F, in this case, is lowercase f. And if I wanted to relate the capital F back in a different manner, the antiderivative of this derivative function takes me back to here. So that's what an antiderivative represents. Now let's go look at this a little bit farther. We're going to use Desmos and look and see some things here. Okay, so here we have the graph of some derivative, all right, and it's in red. And as we see, it's a linear equation. We're going to let that be lowercase f, so that way it kind of matches what it is we're looking at in our notes for the fundamental theorem of calculus. And we're looking at the area up underneath this curve from A to B, which I've selected. If you look at the left-hand side of the Desmos window, I'm going from A to equaling 2 to B equaling 5. And it's shaded in to show that, okay, the definite integral is representing the area up underneath that curve, and we get to be 10.5. Now I'm going to graph the antiderivative of f onto the same graph here, and so it's going to be in green, and so we see the antiderivative of f. We're going to learn how to find this antiderivative here a little bit later in this video, but so I'm seeing the graph here, and I want to compare the area up underneath the curve of f of x dx to values of its antiderivative. So I changed my zoom window a little bit here, and so what I did is I found the values of the antiderivative at x is equal to a, and found the values of the antiderivative at x is equal to b in terms of the y values. And so the y value at f of a and the y value f of b, and we subtracted those two values. And we wind up getting 10.5, which is exact same value as the area up underneath the curve. And what you'll notice here is that as I start moving the a and b values around, that relationship will stay true at all times, where the area up underneath the rate curve is equal to the net change, this big term there, net change in the original function's value. And this green curve that we're looking at is the antiderivative. So what I want to do here is I want to kind of summarize what we just saw, is that the area up underneath the rate curve, which is this definite integral, the rate being the derivative, is equal to the net change in f of x from a to b, which is f of b minus f of a. So now we're going to work our way. We're going to learn how to start finding this antiderivative. All right, we're going to start with some integral formula rules, where we're going to look at integrating constants and even the power rule for integration. And so basically the process of doing integration is undoing the derivative of something. So we're going to keep that in mind here. So let's look at this first problem. And so I want to find the area up underneath the curve from 2 to 5 for 3 times dx. Well, when you're looking at this, what you're trying to do is you're looking at what's inside of here and say, okay, well, what was the derivative what did I take the derivative of to get 3? Well, according to our rule is that if I'm taking the antiderivative of some number, that is equivalent to a times, or that number times x, because the derivative of a times x makes a. So therefore, the antiderivative of 3 would be equal to 3x. Now, if we had an indefinite integral, like in here in our formulas, where we don't have numbers for our lower limits and upper limits of integration, we would have to put plus c, which represents the constant that I could have had in taking the derivative of to make what I have inside of here. However, we have definite integrals, so our answer should represent an area. So we're going to have to plug in to get the area values. Now, according to the fundamental theorem of calculus, that's going to equal what I get when I put in the top number for x minus what I get when I put in the bottom number for x. A little notational standpoint, what we would do is we'd make a little documentation line here, and we're going to put in 2 and 5 inside of our antiderivative to get our answer. Well, we would put 5 in first. You always start with the top number. And then minus, you're going to put in the bottom number second. And so our answer is going to be 3 times 5 minus 3 times 2, which gives us an answer of 9. Okay, now we look here at this next one. So I want to find the area up underneath the curve for just from 3 to 6 for just dx. So I got to think, well, what did I take the derivative of to just get dx here? And a lot of times people get confused. Remember that if you don't see a number in there, it's really a 1. So I took the derivative of some function, and I ended up with 1. So basically the antiderivative of 1, I just put an x on it, makes 1x. So the antiderivative would be x, but because it's a definite integral, instead of writing x plus c, I'm going to evaluate. So I'm going to go from 3 to 6. I put in 6 for x, minus, put in 3 for x. The area up underneath that curve would be equivalent to 3, or my overall net change. Now let's look at the power rule. So the power rule for integration is that if I want to integrate a function x to the n power, what you're going to do is I kind of do the opposite of what I did for when I took the derivative of x to a power. Is I'm going to add 1 to the exponent, so it becomes x to the n plus 1, and then I'm going to divide by whatever that new exponent is. So the antiderivative of x squared would be x to the third divided by 3, and then we're going to have to plug in. So we're going to plug in from 0 to 3 for x, and then we're going to evaluate. So we'd have 3 to the third power divided by 3 minus 0 to the third power divided by 3, and then we would get our answer here of 9. All right, next one. I want to find the value of the definite integral from negative 1 to 8 for x to the negative 2/3 power dx. Well, I still have x to a power. So the way that's going to work is I'm still going to increase the exponent by 1. So I'm going to add 1 to negative 2/3. That makes x to the 1/3. And then I'm going to divide that by its new exponent. So x to the 1/3 divided by 1/3. And then we're going to plug in our numbers. Now that, I'm going to write that a little easier so it's a little easier to work with. That's equivalent to 3 times x to the 1/3 power. And we're going to do our documentation line because we're substituting. We're going to substitute 8 and negative 1 to go get our answers. And so we put in 8. The cubed root of 8 is 2. And then minus 3 times the cube root of negative 1, which is negative 1. And we evaluate that there, and we wind up getting 9. Okay, next one. All right, so here we have 5 times x to the third power dx that I want to find the antiderivative of, and then plug in my upper and lower limits of integration to get the value of the definite integral, or the overall net change. Well, this one we're going to apply the power rule, because I have 5 times x to the third power. So the power rule says I'm going to keep my coefficient here, and I'm going to take x, increase this exponent by 1, and divide by the new exponent power. So it becomes 5x to the fourth power divided by 4. Now we're going to plug in, and we're going to go from 0 to 2 to get the overall area. So I'm going to put in 2 first, so we'd have 5 times 2 to the fourth power divided by 4 minus 5 times 0 to the 4th power divided by 4. And we work to get our answer, and we wind up getting 20. Okay, so new problem here. I want to find the value of the definite integral from 4 to 9 for 1 over the square root of x dx. So in order for us to apply our rules, I need to rewrite the 1 over the square root of x dx as x to an exponent power. 1 over the square root of x is the same thing as x to the negative 1/2 power. So I'm going to do a rewrite so that way I can apply my power rule for integration. The power rule for integration says that the antiderivative of x to a power would be add 1 to the exponent, so that makes x to the positive 1/2, divide by the new exponent. So x to the 1/2 divided by 1/2, well, I'm going to write that a little simpler. That's the same thing as 2 times x to the 1/2 power. And we're going to evaluate this from 4 to 9 to find the area up underneath that curve. So we plug in the top number first. So it'd be 2 times 9 to the 1/2 power minus 2 times 4 to the 1/2 power, which the 1/2 power is simply the square root. And then we evaluate, and we wind up getting an answer here of just positive 2. So now we're going to look at finding the antiderivative, the indefinite integral of 1 over x dx. The antiderivative of 1 over x dx is equal to the natural log of the absolute value of x plus c, where c is some constant. Now just think about what we have. If I took the derivative of the right-hand side, the derivative of the constant is 0. The derivative of the natural log of x is just 1 over the inside. All right, so basically what the antiderivative is representing is what it equals, in what case, is a function whose derivative makes what was inside of the indefinite integral. The antiderivative of e to the x is e to the x plus c, because the derivative of e to the x is itself, and so is its antiderivative. And then we have the case where if I want to find the antiderivative of an exponential function that is not e to the x, all right, we're basically going to end up with that same exponential function times 1 over the natural log of the base plus c, where a is representing some constant. Okay, let's look on the first problem on the left-hand side. So I want to find the antiderivative of 3 over x dx, and I want to, in fact, it's a definite integral. I want to go from 3 to 6. Well, we can use a property of integrals here, and I'll zoom in, where if I have multiplication by a constant, I could take that constant outside of the integral and look at this as 3 times the definite integral from 3 to 6 of 1 over x dx. And then it matches our derivative, or excuse me, our antiderivative formula exactly, where we would have basically 3 times the natural log of the absolute value of x would be the antiderivative. I'm not going to put plus c, because for definite integrals, you don't have plus c. You only do that for indefinite integrals. And so we're going to do our documentation line from 3 to 6. And then we're going to plug in. So we would have 3 times the natural log of 6 minus 3 times the natural log of 3. And then we could wind up getting creative to do some simplifying. And from here, what I could do is remember that the natural log of 6 is the same thing as the natural log of 2 times 3. And then I have minus 3 times the ln of 3. And we can break up multiplication inside of the log as the addition of multiple logs. So I could say it'd be 3 times the ln of 2 plus 3 times the ln of 3. And then I still have minus 3 times the ln of 3. And then we wind up simply with just 3 times the ln of 2. And we could even go one step farther and say, hey, you can take the coefficient of the log, take it inside, and make that just the ln of 8. I could go all the way to there. All right, let's look here at this next one. So I want to find the value of the definite integral from -1 to 1 for 2 times e to the x dx. Well, we could use a property of integration where I can take the constant outside of the integral and evaluate this as 2 times the area up underneath the curve of the e to the x dx. Well, we can go and say, all right, well, the antiderivative of e to the x is just e to the x. And then we're going to go from -1 to 1. And so basically, we would just have 2 times e to the 1 power minus e to the -1 power. And then we would have to simplify that however we would need. And I'm just going to leave this as 2 times e minus 2 over e. All right, next example, I want to find the definite integral from -1 to 2 for 3 to the x dx. And basically, I'm trying to find the antiderivative first. So what function did I take the derivative of to make what's inside of this integral? Well, according to our integration formula, the function that I took the derivative of would be 1 over natural log of the base times the exponential function plus c. Now, because it's a definite integral, we're not going to include the plus c because we're going to actually find the area up underneath the curve and not just an equation. So the antiderivative of 3 to the x would be 1 over the natural log of 3 times 3 to the x power. And we go from -1 to 2. And we would just plug in. So we'd have 1 over the natural log of 3 times 3 squared minus 3 to the -1 power. And everything else would just be algebraic manipulation. And for context of this video, I'm just going to leave it right there and move on. All right, next let's look at some examples of finding antiderivatives and definite integrals for some of our trig functions here. And so remember, so I have them all written here, but basically when I'm taking the antiderivative of something, what it's going to equal is the functions whose derivative I took to make what I'm finding the antiderivative of. For instance, the derivative of sine is cosine, which means that if I'm taking the indefinite integral, or I want to find the antiderivative of cosine, that makes sine. Likewise, the derivative of tangent is secant squared. Therefore, the antiderivative of secant squared will take me back to tangent. The derivative of secant is secant times tangent, which means that the antiderivative of secant times tangent will take me back to secant. So that's what we're really doing here. Let's look here at this first problem. So I want to find the value of the definite integral from pi over 2 to pi for 1 plus cosine of x dx. Well, this is the first one we had, but we've had multiple terms here. So if I have multiple terms, what I can do is I can integrate each piece separately and find their antiderivatives. So the antiderivative of 1, being just a constant, is going to be x. The antiderivative of cosine, so whose derivative made cosine, is going to be sine of x. So I'd have x plus sine of x. Now, because this is a definite integral, because I have lower and upper limits of integration, I'm not going to put plus c. We're having to plug in values. So I'm going to make my documentation line, and we're going to write pi over 2 on the bottom and pi on top. First number you plug in is the top number, so we'd have pi plus sine of pi minus, then you plug in the bottom number, so it'd be pi over 2 plus sine of pi over 2. And then we would evaluate from there, which basically we'd have pi plus 0 minus pi over 2 plus 1. And there's not but so much we could do from there. We wind up getting pi over 2 minus 1. Okay, next one. I want to find the value of the definite integral from 0 to pi over 4 of 2 times secant x tangent x dx. All right, well, I would take this problem here at the very beginning. We're at the onset of learning how to do these. I'm going to pull the constant out. So I'm going to use a property of integrals, pull the constant outside, and we're looking at this problem. Now, 2 times the definite integral of secant x times tangent x dx. So looking at what I have on the inside, I'm trying to think whose function has the derivative of what function makes secant x times tangent x. And that is actually the derivative of secant itself. So I'm going to have 2 times secant of x. And we're going, because it's a definite integral, we got to plug in. So we're going to go from 0 to pi over 4. You plug the first number in first, so it would be 2 times secant of pi over 4 minus 2 times secant of 0. And then we get those values off of our unit circle. So we would have 2 times secant of pi over 4 is the square root of 2. And then minus secant of 0 is 1. And so basically, we would just have 2 roots of 2 minus 2. Okay, next one. We want to find the definite integral from 0 to pi over 3 of secant squared of x minus sine of x dx. Well, we have two functions in here, so we could break this up into two separate integrals, evaluate and put them together. We could just find the antiderivative of each term and do it all at one sum. So I start by figuring out whose the derivative of what function will make what I'm looking at here. So I'm trying to find the antiderivative of what we're looking at. The antiderivative of secant squared is tangent of x, because the derivative of tangent makes secant squared x. So I'm going to have tangent of x, and then what function's derivative makes sine of x? Well, in fact, the derivative of positive cosine of x would actually make negative sine of x. So I would turn this into plus cosine of x. And always do a quick check to make sure you did it right. Derivative of tangent makes secant squared. The derivative of positive cosine makes negative sine of x. So far we're good to go. Now we're going to plug in. We're going to go from 0 to pi over 3. And we put in pi over 3 first, so we'd have tangent of pi over 3 plus cosine of pi over 3. And then minus, we're going to put in our lower limit here, so it'd be tangent of 0 plus cosine of 0. And then we go get our values here off of from our unit circle. Tangent of pi over 3 is the square root of 3. Cosine of pi over 3 is a half. So that's the first part. Minus tangent of 0 is 0. Plus cosine of 0 is 1. And we wind up getting just the square root of 3 minus 1. Okay, lastly here, we are going to find the antiderivatives of our inverse trig functions. So the antiderivative, or the indefinite integral of 1 over the square root of 1 minus x squared dx is the inverse sine function. So basically what you're looking at, the derivative of the right-hand side here, the derivative of inverse sine makes what's inside of the integral. The derivative of inverse sine is 1 over the square root of 1 minus x squared. So we're just going in the other direction. Remember that. Therefore, the antiderivative, or the indefinite integral of 1 over 1 plus x squared, is the inverse tangent function. Basically, the derivative of inverse tangent is 1 over 1 plus x squared. And the same thing for the inverse secant function. The antiderivative of 1 over the absolute value of x times the square root of x squared minus 1 makes inverse secant of x plus c. If I took the derivative of inverse secant of x, it would make what we have inside of here. So let's do a couple of examples. We'll start here on the first one. The antiderivative, or excuse me, the definite integral from a half to 1 of 2 over the square root of 1 minus x squared. Well, I want to make that look exactly like our antiderivative formula. So I'm going to take that 2, and I'm going to pull the 2 outside of the integral. And I'm going to rewrite. So I'd have 2 times 1/2, going from 1/2 to 1, of 1 over the square root of 1 minus x squared dx. Now we're looking at what we have inside of here. That antiderivative would be the inverse sine of x plus c, but I don't include the plus c because we're doing definite integrals because we have numbers there. So what that is going to equal would be 2 times the inverse sine function of x, and we're going from 1/2 to 1. And we go evaluate. So basically we would have 2 times inverse sine, and we'd put the top number in first, so inverse sine of 1 minus inverse sine of 1/2. And we need to evaluate that. Well, when evaluating inverse trig functions, you got to remember the range. The range of inverse sine is the right half of our unit circle, where we go from negative pi over 2 to positive pi over 2. That's what it's allowed to output, right half. Well, where does sine equal positive 1 at on the right side of our unit circle? Well, sine equals positive 1 at pi over 2. And then minus, where does sine equal 1/2? Because that's what you're asking yourself when you're evaluating this. Inverse sine of 1/2, sine equals 1/2 at at pi over 6. So there would be our answer there. And that winds up simplifying just to make 2 pi over 3. All right, so new problem here. I want to find the value of the definite integral from -1 to the square root of 3 of 1 over 1 plus x squared, where that matches exactly to our antiderivative rule here, our integration formula. That it just simply makes the inverse tangent function. So I would write the antiderivative, which would be the inverse tangent of x. And we're going to go from -1 to the square root of 3. I don't include the plus c on the end because we're doing a definite integral. So I'm going to put in the top number first. So it'll be the inverse tangent of the square root of 3 minus the inverse tangent of -1. I got to remember the range of inverse tangent. When I'm doing this, the range of inverse tangent is the right-hand side of the unit circle as well, where it can only output values from -pi over 2 to +pi over 2. The trig functions that output, or inverse trig functions that output on the right half of the unit circle, are going to be inverse sine, inverse tangent, inverse cosecant. The inverse trig functions that have ranges on the top half of a unit circle from 0 to pi radians are cosine, secant, and cotangent. So I need to keep that in mind there. So we're back to evaluating. So inverse tangent of the square root of 3, I got to think about, all right, well, where does tangent equal positive square root of 3 at on the right-hand side of my unit circle? And that happens at pi over 3 radians. Minus, I got to think about, well, where does tangent equal -1 at on the right half of my unit circle? Well, that would be at -pi over 4. And so we'd have to evaluate pi over 3 minus -pi over 4, and we wind up getting 7 pi over 12. All right, so looking at this problem here, I want to find the value of the definite integral from -1 to +1/2 of this function. Well, it resembles that of the inverse secant function. So if I pull out the -3, and then I start rewriting, say, all right, well, let's go from -1 to 1/2. I'd make +1 divided by x times the square root of x squared minus 1 dx. And then we would keep going and say, well, wait a minute, this would just be inverse secant, and we would go forward and work from there. Now, here's something that we have to keep in mind. Remember that according to the fundamental theorem of calculus, in order to use the fundamental theorem of calculus, the evaluation part, where I want to find the area up underneath the curve from A to B, this function here has to be continuous for every value from -1 to +1/2, including the endpoints. Well, we have a problem here. If I put in 0 for x, I'm undefined. And so since we're not continuous at x is equal to 0, we're undefined there. What we have, this is actually called an improper integral. Therefore, I cannot necessarily just apply my fundamental theorem of calculus. We would have to determine if the limit of this will converge or diverge in order to answer it. This is something you learn about later. It is important to keep in mind the requirements. You have to be continuous from A to B in order to apply the fundamental theorem of calculus. So here we cannot apply the fundamental theorem of calculus because we're not continuous at a number inside of this integral.